Hello everyone. Today we're going to talk about how to sketch the Nyquist plot and how to determine stability using the Nyquist criterion. Before we get into how to sketch and how to determine the stability, um, we should know that the main idea behind the Nyquist plot and the Nyquist criterion, the main advantage that we get from this is that we can determine the stability from the open loop transfer function. So before we close the loop, we can determine if it will be stable or unstable after we close the loop. So let's get right into it. The first step is we want to rewrite our open loop transfer function in Bode form. So if you just take g of s as s plus 3 divided by s times s minus 5 and k equals 2, you're going to get the open loop transfer function written here, denoted by L of s. The next thing is we want to get the phase Bode plot from this open loop transfer function. So we could see that after I've completed the Bode plot, we get the phase that starts from negative 270 degrees. Degree sign. So from negative 270 to negative 90 degrees. Now, why do we care about this? Well, for our next step, we need the Nyquist range. I just call it the Nyquist range. Basically, what this is going to tell us is the range in which we plot our Nyquist, like in which we sketch our Nyquist plot. So here we got negative 270 to negative 90, or pi over 2 to 3 pi over 2. I'm just going to skip step 4 and show you guys. So pi over 2 is here and 3 pi over 2 is down here. So we know that it's going to be in quadrant number 2 and quadrant number 3. This is just not going to have anything over here. So it gives us a bit of information on where we need to draw the plot. I'm going to remove them. Okay. After we found our Nyquist range, we need to determine 3 crucial points. So first, you put it in polar form. We had the Bode form, and after doing some algebra, you can get the polar form like this. Then you need to find 3 major points or critical points. The first one is you want to see when the imaginary axis is at 0, so you can find the intersection on the real axis. We reject the pole and the value of omega less than 0 because we can't have negative omegas. So we take the root 15, square root of 15, and we put it into the real of the open loop transfer function, and we get negative 0.4. So this is our first point, negative 0.4 and 0. So over here, we have negative 0.4 and 0. Then our next point is going to be limits of omega approaching infinity and 0 plus. You do that for the imaginary and real. So we get, for infinity, we have 0 and 0. And for real, we have infinity and negative 0.64. So after we've collected all these points, the last, before last step, technically the last step for sketching is to just draw it. So we have, let's see, we have when omega is 0, we have j omega to infinity. So over here, let's just say this is omega equal 0 plus. So we're at infinity, and our real is at negative 0.64. I'm just going to shift it a little bit, be a bit more accurate. Say it was here. Okay. And then at infinity, omega infinity, we are at the point 0, 0. So omega equals infinity, we're at 0, 0. Now keep in mind that we know we have to intersect the real axis at negative 0.4. So we go from this point to this point because we always go from negative infinity to 0 minus. This is kind of my trick. And we go from 0 plus to infinity. This is a very important step, actually. It's a trick that works for me. I'm just sharing it with you guys. but it's actually very important, and I'll show you guys why. So negative infinity to 0 minus and 0 plus to infinity. So 0 plus to infinity, and we know we have to intersect this point here, and we go to omega equals infinity. So from 0 plus to infinity, so draw your arrows this way. We know we're going this way, okay? And now the last step, or before last step here, is that we have to draw a reflection of this. So if omega infinity is at 0, then omega negative infinity is also at 0. But since we have we're at j omega equals infinity for 0 plus, then for 0 minus, we're going to be at, this is 0 minus, sorry, 0 minus, we are at, we're over here. So technically like negative infinity of the j omega. And now we know that we have to go from negative infinity to 0 minus. So our negative infinity is over here. Again, intersect the intersection point here and go over to 0 minus. I hope this makes sense. So we went from negative infinity like this, negative infinity to 0 minus, and we went from omega equals 0 plus to omega equals infinity. So we have these arrows, right? Now, the last step for sketching the plot is look at the sign of the gain. It's negative. Whenever it's negative, we go counterclockwise. If it's positive, we go clockwise. So we want to connect our two dots, and we go counterclockwise like this, where the radius, okay, technically the radius is infinity from the intersection point, or sorry, the intersection point's over here. So this is a radius of infinity. I'm gonna remove it. You could just, this is just a sketch. So yeah. Now for the last step, oh yeah, we could also draw our arrows. This is also very important. Oops, like this. Okay, there we go. For the last step, we have the Nyquist criterion to determine the stability. The Nyquist criterion says that if z is equal to 0, then the closed loop function is, or the closed loop transfer function is stable. So to determine what the value of z is, we do z is equal to n plus p. N is the number of clockwise revolutions around the point -1 over here, and j0, and we see that we do one clockwise revolution. If we did a counterclockwise revolution, then it would be -1. But because we have one clockwise rev around this point, it's just n equals 1. And from the open loop transfer function, we have the pole right here, s minus 5. The pole is at 5. So s equals 5 is a pole. This is unstable because it's on the right side of the imaginary axis. And so we have one unstable pole. Now 1 plus 1 is equal to 2, which does not equal 0. So by the Nyquist criterion, we know that, that's it. From the Nyquist criterion, we know that the closed loop function, transfer function, is unstable. Just leave it like this. That's it. So it takes a bit of time to do all this work. I'd like to mention a couple things. Firstly, I only drew the phase mode plot. You could also draw the magnitude and skip like step 4, because you could do it graphically. I like to be a bit analytical, so I plug in small values of 0 to obtain my points. And yeah, that's pretty much it. After that, you sketch your plot, and you can determine the stability using the Nyquist criterion. That's it for this video, guys. Thank you very much, and like and subscribe, and I'll see you in the next one.